Okay, so we're recording so we will start now with the last discussion of our relativistic hydro and holography focus week. And of course, last but not least, it will be Alex Serantes talking about the hydrodynamic gradient expansion meaning with less symmetric fluids. And of course, we've heard lots of things about what you will do. So everyone is very excited to hear you.
Yeah, I realized that this discussion session was advertised by my collaborators a few times. So my plan for this is to share with you some ongoing work, which is done in collaboration with Michał Heller, Michał Spaninski, Victor Svensson, and Ben Withers, and use these results that I'm going to present as a way to ignite a discussion on the general questions that they try to address. Okay, so as it says here, the topic of the presentation I'm going to give is that of the hydrodynamic gradient expansion beyond highly symmetric fluid flows. By this term, you can have in mind Bjorken flow. Okay, so just to put everybody on the same page, I have this introductory slide telling you what the general context in which this problem is embedded is. So we're going to be discussing about hydrodynamics, and as it has been emphasized repeatedly during this week, hydrodynamics is extremely important from a scientific standpoint because it provides an effective description of the late time and long range behavior of any continuous medium, which is endowed with conserved quantities, in particular with a conserved energy momentum tensor. And this effective framework is extremely powerful, and it can be employed to describe phenomenology, let's say, the collective behavior of QCD matter or condensed matter systems. And it's fair to say that despite the scientific importance of hydrodynamics and its long history, there are still fundamental aspects of it that are waiting to be fully understood. And this is the case when stochastic fluctuations are present in your system and you want to incorporate them into your hydrodynamic description. And we ended this morning discussion session talking about this very topic. But it's a comment that it also applies to the situation in which stochastic fluctuations can be neglected. So I will refer to this scenario as classical hydrodynamics, and as Michał beautifully put in his talk on Tuesday, classical hydrodynamics is just a classical field theory with dissipation, okay? And in this talk in particular, we are going to be focused on one of these fundamental open questions of classical hydrodynamics, which is the large order behavior of the hydrodynamic gradient expansion. And I will define what I will mean precisely by the hydrodynamic gradient expansion in a while, okay? So at least from my personal viewpoint, the interest in studying this particular question comes from the fact that relativistic hydrodynamics, when truncated to low order, I mean, when keeping only the first or second order corrections in gradients, have been shown to be unreasonably effective in a variety of physically relevant setups. This meaning that it works very well even if the system has not yet achieved local thermal equilibrium and the typical size of the gradient corrections is not particularly small. And it has been suggested by some authors in the past that this feature could be explained by the divergent character of the hydrodynamic, of the sorts of the types of gradient expansions that hydrodynamics would give you, by the fact that maybe the first few orders of these expansions, which work remarkably well, are just happen to be close to the optimal truncation of the series. So the idea here would be to explain this unreasonable effectiveness as an example of Carrier's rule in action, okay? So this is the question we're going to focus on. And as was reviewed by Michał on Tuesday, I would say that by now we have a well-developed understanding of how the gradient expansion behaves in highly symmetric fluid flows, in particular Bjorken flow, across several models of physical relevance. The common feature of these models would be that they involve systems of partial differential equations, or as it is the case of kinetic theory, perhaps systems of integral differential equations. And among other facts, as the main highlights of these studies that I would put here, and if you have some other point that you want to emphasize, please interrupt me and say it. So, okay, so these studies first have demonstrated that the hydrodynamic gradient expansions can be factorially divergent asymptotic series. And they have also provided us a detailed understanding of how the large ordered behavior of these gradient expansions is encoding information about the transient non-hydrodynamic modes present in your microscopic theory. So the large order behavior of the gradient expansion, as it's very well known now, encodes information about the transient contributions to the energy momentum tensor. Okay, and in particular, just to reiterate for Bjork and Flo, this is a connection, which is precisely a connection between, let's say, singularities of the Borel transform of the gradient expansions that people consider in the Borel plane and the non-hydrodynamic modes of the system at zero spatial momentum. Okay, this has been developed in many papers by the people in the audience here, including Michal Spalinsky, Michal Heller, Ines, and so on. So in this talk, okay, well, regarding the question of breaking free from the symmetric restrictions, so Ben discussed in his talk yesterday what we understand now about the hydrodynamic gradient expansion for conformal fluids in the linear response regime. And based on these two different areas, different past developments, the natural research program that would suggest itself is to bridge the gap between them, right? So we will need to understand how the properties uncovered for boost invariant expanding fluids extend to situations with less symmetry assumptions. So here are some of the questions that we would like, or I would personally like to have answers to. So the first one, we already discussed this morning, but I want to emphasize it again because I think it's very important. And is it that, do we always need a transseries representation to deal with the gradient expansions that hydrodynamics provides to us? Are these gradient expansions guaranteed to be factorially divergent asymptotic series for a generic fluid flow? And this is particularly relevant because we are aware of situations, as illustrated in this paper by Gabriel Nicol and George Noronha in 2019, in which the gradient expansion is actually a geometric series and can even be convergent in some parametric regime. So is there a well-defined sense in which these examples are fine-tuned? That's my complementary question to this more general question. And now, assuming that the factorial divergence is present, we would like to understand the origin of this divergence. In the language that Michal put forward on Tuesday, is this divergence renormal-like? I mean, is it due to the fact that at a given order in the gradient expansion, there are particularly terms that grow factorially and those give you the overall factorial divergence? Is it instanton-like in the sense that you have a factorial number of independent terms contributing at each order in gradients, and this is the underlying cause of the factorial divergence of the whole gradient expansion? Are we actually in front of a combination of both effects? You can wonder whether the existence of the factorial divergence would be a property of the microscopic theory and would be encoded in the number of independent terms that you have to consider and the values of the large order behavior of the transport coefficients, or would its present also be dependent on the particular solution you are employing to compute the gradient expansion? And in general, we would also understand, more generally, assuming that we have a factorial divergence present, a complementary question to this question of its origin is understanding what is the relation between the singularities of the Borel transform of this gradient expansion and the non-hydrodynamic modes present in your system. So we would like to understand how this connection, which was uncovered for Bjork and Flo, would extend to more general fluid flows. So in this talk, I will show some preliminary results that try to address directly some of these questions. And this is work in progress, I have to say. And we only have a relatively decent and well-developed and relatively developed understanding of the case of BRS3 theory. So I will focus on this particular model only, and I will comment on generalizations of some more of our results to other models, in particular to ADS-CFT, only at the very end of the talk. So if you have any question, comment, point that you want to add, clarification you want to be made, etc., please do it now, because then I'm going to get into more specific details of what I'm going to say.
So can you clarify a little bit what exactly you mean by renormal-like and instanton-like?
Yeah, so I have an extremely limited understanding of this topic, but my understanding is that in perturbative quantum field theory, non-perturbative effects, which would correspond to instantons, would manifest themselves as a factorially growing number of Feynman diagrams contributing at factorially growing with the order, but the renormal on light would be some individual diagrams growing factorially. So that's what I have in mind.
I see. That's what you mean. I mean, typically, I would say the renormal on light contributions are due to the running coupling, and whether the typical analysis in terms of these bubble diagrams and is not actually very rigorous, but I see what you mean. It's just you use as some sort of like to classify the combinatorics of the.
Yeah, but you can say that. Yeah,
it's like a it's like a mnemonic more than I see.
Yeah, but okay, but you're saying that this terminology is perhaps not the optimal.
Yeah, but okay, I just want to understand what you mean. But yeah,
sure. No, but it's good to know because yeah, I have a very limited understanding of this particular topic, so I just use it as a catchphrase to synthesize what I meant, basically.
I think it's in the last discussion what Mikhail also pointed out that the way that the factorial appears is not the different sort of ways of sort of the combinatoric ways of creating these large order terms, but from the number of perturbations standard. Is it somehow related to Mikhail's comment?
Yeah, I would say that I meant basically that, if I understand you correctly.
Okay. Yeah, thanks.
Okay. Okay, good. So any other comments, questions? Should I continue? How do you put this in, by the way? Is there any way of putting this in full screen mode?
Like with view?
No.
No.
Yeah, view full screen. Maybe this. Okay.
Right.
That's better. Yeah, that's better. Okay, so I would continue, and just to emphasize, just to be sure that everybody is on the same page, I'm going to define now what I mean by the hydrodynamic gradient expansion in this talk. Okay, so we are going to imagine that we have an expectation value of an energy momentum tensor, and that we are expressing it in an Arnaud frame as it is standard in terms of a perfect fluid contribution, which is fixed in terms of the energy density of the fluid and the normalized fluid velocity, and a correction, which I'm going to be referring to as the dissipative tensor, or the tensor of dissipative currents, which encodes deviation from perfect fluidity. Okay, and in this talk, we are only going to consider conformal fluids, so that this stress energy tensor is going to be traceless, which implies this very well-known equation of state relating the pressure and the energy density, from which you can extract directly the conformal speed of sound, and also implies that this tensor of dissipative currents is traceless. So the main object we are going to focus on are the constitutive relations, which are going to express the dissipative tensor as a functional of the elementary hydrodynamic fields, energy density and fluid velocity, and including here possible space-time derivatives of these objects. So these constitutive relations are, of course, explicitly tractable in several limits. So one limit would be linear response theory, and this has been extensively explored by in a series of works starting by Wu and Lublinsky in 2014, or hydrodynamics. So what I meant here is that we are going to, by hydrodynamics here, is that we are going to think of classical relativistic hydrodynamics as the effective field theory, which is defined by the constitutive relations giving us a gradient expansion acting on the elementary hydrodynamic fields, energy density and fluid velocity for us. And the equations of motion of the theory, besides this gradient expanded constitutive relations, are just energy momentum conservation. Okay. So the question we were going to try to answer is, what is the larger behavior of this gradient expanded constitutive relations, which from now on is going to be the hydrodynamic gradient expansion for us, when acting on a particular fluid flow? And we are not going to discuss at all the initial value problem in this particular theory. Okay, we are going to forget about this topic altogether, and we are going to focus on the operational question that, assuming that you know the gradient expanded constitutive relations, and somebody gives to you the energy density and the fluid velocity, can you tell me what the tensor of dissipative currents is? That's the operational question that we have in mind, okay? And an important comment on this front is that when working at the level of the gradient expansion, it's always possible to employ the equations of motion, the conservation equations of the energy momentum tensor, to replace time derivatives by spatial derivatives in a systematic way. And this was exploited in Ben's talk yesterday to construct a purely spatial formulation of the gradient expansion of the constitutive relations, because in this particular language, in this particular formulation, it's making connections with momentum space dispersion relations is the easiest. But here we are not going to adopt this strategy by default. Okay, that's also a clarifying comment I want to make. Okay, so our focus in this work is going to be BR3 theory, which, in case you don't know, I guess that most of you know this, but I'm just going to repeat it for completeness. So this is a phenomenological model that, besides the energy density and the fluid velocity, also treats the dissipative, the tensor of dissipative currents, the dissipative tensor, as a set of independent dynamical degrees of freedom. And the ultimate reason behind this choice is being able to embed second-order relativistic hydrodynamics in a framework which is compatible with relativistic causality. Okay, this is not the only way of achieving this goal, and in recent years, alternative first-order formulations based on the choice of generic frames other than the Landau frame have been extensively explored. Maybe with some people, I don't know if George is in the audience, so he has worked on this extensively. But in any case, we are just going to choose this particular theory as a benchmark model in which we can try to play around with our ideas, okay? So as I said, pi mu nu, now it's a dynamical tensor field, and in particular, it obeys this relaxation equation. So this relaxation equation is basically an equation which tells you that pi mu nu here reduces to its value predicted by second-order hydro, but the second-order hydrodynamic gradient expansion. Here I'm just representing the first-order terms, but the second-order terms can be incorporated with no problem. Okay, so it just tells you that pi mu nu relaxes to its value as predicted by the hydrodynamic gradient expansion of the constitutive relations on a time scale set by this parameter tau pi, which is called the relaxation time. Okay, so this tau pi is the relaxation time. This is just a co-moving velocity, a co-moving derivative. You don't have to worry about it. Pi mu nu is the dissipative tensor, sigma mu nu is the shear tensor, and eta is the shear viscosity of the system. And we are going to, in this part of the talk, we are going to be dealing with a conformal fluid. So just by dimensional analysis, we know that the shear viscosity has to scale as the temperature of the fluid, the local temperature of the fluid to the third power, and the relaxation time has to scale like the inverse of the local temperature of the fluid. And when I say local temperature of the fluid, I just mean that for a conformal field theory, in thermal equilibrium, the energy density is given in terms of the equilibrium temperature as is proportional to T to the fourth. Okay, so we are just going to define T out of equilibrium, assuming that that relation holds. So this T here is defined in terms of the out of equilibrium energy density. Okay, which, due to our choice of Landau frame condition here, is just a particular component of the energy momentum tensor. Okay. Okay, so I assume this is clear to everybody, but if you have any question, please do it now, because I don't really want to come back to this.
Sorry, I have a very stupid question. Okay, when you say conformal, how did you make sure all of conformal algebra is satisfied?
Sorry, how do I make sure?
All of conformal algebra is satisfied. Conformal is simply like a special conformal rotation or whatever.
Yeah, it's through this. This is a bicovariant derivative which takes into account that this object transforms in the correct way under Euler scaling symmetric.
So yeah, it's only wide scale, right?
Sorry?
It is only wide scale, yeah, dilatation, roughly speaking, right?
Nah, sorry, I didn't get that. Can you repeat the last part of what you said?
Okay, so it's only the kind of dilatation, right? So, for example, if you see the torus condition, okay, it's a condition for the.
I think it would take into account any coordinate transformation that rescales the metric by some space independent function, right?
And also the special conformal or whatever.
Yeah,
right?
I would say so. Yeah.
Okay.
I would say so. Okay, so great. So, okay, so now this is the main new input. So now what I said before was no, this is the main new input of this particular talk, as far as I know, which is that we are going to be studying 1 + 1 dimensional longitudinal flows in this theory. So what do I mean by this? So what I mean by this is that we are going to consider a fluid flow will live on a background Minkowski spacetime, given with this metric. And the flow is going to be described by an energy density, which is going to be a function of t and x, and a fluid velocity, which is expressed in terms of this field, space-time t and x dependent field, small u, in this functional form, so that we make sure that this is unit normalized with respect to the norm prescribed by the Minkowski metric. Okay. So our fluid, so the perpendicular directions are still spectator directions. They play no role in the description of the system. And our fluid lives in this 1+1 dimensional reduced spacetime. But we are not going to assume that is boost invariant, okay? So this is, if you want, this is, you can think of this fluid as a particular nonlinear sound wave. And if you want, this is the most immediate generalization of a boost invariant flow, because you're only breaking one particular symmetry fit, right? Okay, so for such a simple flow, the dissipative tensor, which has to be traceless and transverse to the fluid velocity, can be parameterized in terms of only one independent degree of freedom, which is this pi perp component here, which we also take to be a function of t and x, okay? Okay. So in order to obtain the gradient expansion of the constitutive relations, what we are going to do is to introduce, this is also the strategy that Ben mentioned in his talk at some point, we are going to introduce a formal parameter epsilon by means of a homogeneous spacetime rescaling, okay? And we are going to put forward the following ansatz for this pi perp field, which is just a particular component of the dissipative current tensor, okay? So we're just going to assume that this pi perp field is a formal power series in this fictitious epsilon parameter, whose components are space-time dependent functions. Okay, so then you can perform this. You can perform this rescaling in the equation of motion for pi mu nu in BRS3 theory. You can plug in these ansatz, and then you can solve recursively. And what you find is that the first term is given in terms of the shear viscosity and the expansion of the fluid flow as this here. And the remaining higher order terms satisfy this particular recursion relation. So we know the form of this recursion relation, including second order terms in the equation of motion for pi mu nu, but here I'm just not putting the formula, writing the full formula to avoid clutter. Okay. Okay, so we have this expression for pi perp, and the question we're interested in is determining the behavior of these coefficients as n goes to infinity at a given spacetime point. And our approach is going to consist of a combination of analytic arguments and numerical experiments that, as we will see as I go, complement each other. Okay, so I'm going to give you the analytic argument first, and it will go as follows. So analytically, we can put forward the following large order ansatz. So we can assume that when n goes to infinity, pi perp is asymptotic to this factorial over power ansatz, okay, with some prefactor, and then you will have 1/n corrections here, which I'm not representing. Okay, so if we substitute these ansatz into the recursion relations and we compensate the dominant terms when n is taken to infinity, what we find is that this field chi here, which would control the location of the singularities in the Borel plane of the Borel transform of the gradient expansion, obeys this equation of motion. So the derivative of this object along the flow is given by the inverse of the relaxation time evaluated at the local temperature. Okay, it's a very simple equation. And for Bjorken flow, I have to say that this is precisely the leading order behavior. This is precisely the behavior that you would expect. And I should also mention that in BRS3 theory, for a sound channel fluctuation, you only have one non-hydrodynamic mode which obeys this property. So the non-hydrodynamic mode at zero momentum is given by the inverse, is set by the inverse of the relaxation time at the particular temperature of the thermal equilibrium state you're considering your fluctuation is perturbing. Okay, so the expression here can be written alternatively in terms of this non-hydrodynamic mode evaluated at zero momentum. Okay, so this is the relation that we find by this analytic argument.
Excuse me. So I want to make sure one thing. So now you introduce the epsilon, right? So and take expanding around extremely equal to 0. So it means large T and large X, right? Roughly
It means
speaking.
large space-time scales, homogeneous in space and time. Yeah, absolutely.
Okay, thank you.
Absolutely. Yeah. Yeah, absolutely. Yeah, this was brought also in the discussion session. I think it was during Ben's talk and also in the discussion session this morning. This is just a formal parameter which has no physical meaning. So in the end of your computations, you want to set it equals to 1. So you introduce it, you employ it as a counting parameter, and then you remove it. That's it. That's the strategy. Okay, so any question about this argument here? Okay, I can see no question, so I will continue. Great. So, okay, yeah. Okay, so by the way, an important point to draw from this analytic argument is that if you look at the equation of motion satisfied by chi, you can actually, well, it turns out that these terms, the second order terms that will be present here, which I'm not writing down for notation for simplicity, actually do not affect this equation. So they would enter into the computation of this prefactor, but it wouldn't affect the particular form of chi. Okay, so these terms, at least this analytical argument, would suggest that these terms are not necessarily to support this factorially growing ansatz. Okay, of course, this is just an analytic argument, and the question you have to ask yourself is whether this behavior that this argument predicts is actually realized in practice. Okay, and this is basically what Ben mentioned at the end of his talk yesterday, in which he showed you some examples. So let's elaborate on those. Okay, so the strategy we are going to follow here is to solve the BRS3 equations of motion numerically, starting from some initial data, which are given by some initial temperature profile, initial pipe perp profile, and initial velocity profile encoded in this U function here. And once we have this numerical solution, we are going to evaluate the recursion relations that we have here numerically to construct the gradient expanded constitutive relations acting on our solution. Okay, so that's the strategy. It's important to keep in mind that since we are, in order to achieve this goal, we are solving our equations of motion on a computer, and that requires that we introduce a grid in a spacetime. Due to the presence of the grid, there is a maximum frequency that your system can support. So if you do this computation and you push it to really large n, what you're going to find is that the coefficients that you obtain do not grow factorially, but grow geometrically. But that's just an effect of the lattice discretization. If you take the lattice discretization to vanish, if you take the continuum limit, if you take your grid spacing to go to 0, what happens is that an intermediate region that's going to be present and that's going to display factorial growth is going to be blown up, and you're going to be left with just that. Okay, so we are interested in this intermediate region. We are not interested in we're interested in how this intermediate region behaves as the lattice spacing goes to 0. We're not interested in what happens when n goes to infinity for fixed lattice spacing. Okay, I hope this point is clear. It's a technical comment, but I think it's important to keep in mind. Okay, so once the dust settles, so if we follow this strategy, okay, once the dust settles, we find that actually it's possible to show that the numerical analysis confirms the analytic prediction. Okay, so what do I mean by this? So first, here you have a plot of let's focus on the, by the way, can you see my cursor when I move it or not?
Yes.
Yes, good. So, okay, let's focus on this plot here. So this is a plot of the ratio test as applied to the coefficients of our gradient expansion as a function of the order, okay? And you see several curves in this plot, and interpretation of these curves is as follows. So the black one corresponds to our initial time. It's not particularly important what the initial time is. It's just some starting time. And the orange one corresponds to the final time. So what we see, first of all, is that for a given time, we actually get a line, we get a linearly rising behavior in this curve, which translates directly to a factorially growing behavior for the coefficients of the gradient expansion. And furthermore, as time goes by, the slope becomes smaller. Okay, so the slope, if these ansatz were correct, would be given in terms of the chi of the smallest chi function present in your solution. Okay, it would be basically the inverse of this quantity. So what happens is that if for this particular example that I'm considering here, it turns out that we can extract this chi function from the slope of these curves. We can plot it, and apart from some boundary effect, which is related to the grid discretization and which would vanish and would go away if the grid discretization were going to be removed, you see that the numerically determined chi by this method for this initial data would agree with your analytic prediction, which is given by this equation here. So the way to see this is that you basically integrate this along a particular fluid flow line, you take the left-hand side, and you just choose a point here, in this case is the middle point, and you correct for the offset. And then you see that the agreement is exceedingly good, okay? So this initial data actually behave in a way that conforms with the prediction of this analytical argument that I show. And of course, this very nice matching between this chi function and the slope of these curves is specific to this particular initial data. In general, this is not guaranteed to happen. And the correct strategy to follow is to compute the Borel transform of the gradient expansion. And once you have the Borel transform of the gradient expansion, you follow the standard algorithm of computing its Padé approximant and analytically continue it using this Padé approximant. Okay, so as you know, singularities of this Padé approximant are poles because the Padé approximant is a rational function, but these poles would arrange themselves into lines of pole condensation, right? Which start at the locations of the would-be branch points of your actually analytically continued Borel transform, right? So what I have in these plots are basically these starting points of lines of pole accumulation, right? So for the initial data that I presented to you, basically at the initial time, you would have this dominant singularity and these other two complex conjugated subdominant singularities. And what you see is that as time goes by, as you move along your flow to the future, these singularities move. This is represented by the progressively more orange color of these points in the plots. And the way it moves, okay, if you believe that this equation actually describes what is going on, you would see that these singularities, which correspond to chi, have to move in such a way that the imaginary part stays constant while the real part increases in a particular way. And this is precisely what you find. If you correct for the expected growth of the real part of these singularities with time, you would see that they actually collapse, well, to some very distant degree of approximation into the same points, okay? So this is a very direct demonstration that the formula that the analytical argument gives to you actually works in practice. And I have to say that I've chosen this example because it is particularly simple, but if you want to see some diabolical ones, you can ask Victor for them. And, and yeah, that's it. Another point which is important to mention is that while we don't understand yet how the singularities you have in the Borel plane are set in terms of the initial data. So if you ask me, why on earth do you have one real singularity and two complex conjugated ones? I have no idea why. I don't know. This is a point that we still need to understand. Okay, so I think I would stop here and I would be glad to hear your comments and answer your questions.
Yeah, thanks for that. That's very interesting. I just have a quick question about this slide, actually.
Okay, great. Go ahead.
Yeah. So just like maybe a small technical question. So why do you use the symmetric Padé approximant and not? So I mean, in principle, what's the logic behind that?
Yeah. Okay. Yeah, you're absolutely right. I wanted to remove the symmetric Padé approximant comment, but I forgot. I use the symmetric Padé approximant, but there's no particularly good reason for doing that.
Okay.
Okay. Yeah. Sorry.
No. I was just curious. Okay.
Yeah. No, there's no fundamental reason for doing that. Yeah.
Can I say something on that? Just that
Sure.
I experienced when you start playing around with non-symmetric ones, it seems that the symmetric one actually seems to behave better with relation to spurious poles. often, not always, but
that conforms with my experience. But also if you offset it a little bit, right? If you just that can also help sometimes.
yeah.
So oh, by the way, yeah. Since there is no rule, a systematic rule that you can use to choose one over the other, right? It's just a matter of trial and error.
Meaning in terms of theorems, which I don't.
Well, in terms of a physicist rigor of level would work for me, right?
But I to be honest, it's just that the spurious poles seem to be quite often leveled with the zeros at the same place. So actually you find that there's no residue associated to them. And if you start offsetting, you might not get this balance when the poles are spurious. This would be my very, very naive answer to that. Sorry.
No, it's okay. It's okay. It's okay. I would definitely love to learn more about, the proper use of Padilla approximants and also the known alternatives to them, if there's any, which I don't know.
It's the whole Pade approximant story is an open book for many things. Can I ask a question as well? So what's the time length?
The time length. Okay, so here, you shouldn't attribute a very deep meaning to so the time interval here goes between 0 and 1. But you have to compare the time with the intrinsic time scale of your system, which is the relaxation time, right? So the relaxation time for this particular example I'm showing here is, if I remember correctly, 0.1.
Okay.
The dimensionless relaxation time, meaning the relaxation time in units of the local temperature of the fluid. Okay. But the local temperature on this particular example is approximately, it has a very weak spatial dependence. Okay, so you can think that the relaxation time here in this particular example would actually be 0.1 in seconds. Okay, so this simulation spans several relaxation times.
So about 10 times.
Yeah, so you cannot consider that this is a short time effect. Okay, so it would include late time, what you would call a late time region.
Thank you.
Okay, welcome. Yeah, I didn't want to include the initial data that I am using because I think they basically add nothing to the discussion. They're just noise that you have to pay attention to. So I just prefer to show the example. But
actually, about that, is the initial condition anything? Meaning, did you have to worry too much about how?
So the question you have to worry about from a technical perspective is convergence. So the point is that for some initial conditions, as you increase the resolution, the terms of the gradient expansion that you're computing converge at very, very different rates. Depending on the initial condition, the convergence can be very fast or very slow, right? So you have to make sure that the convergence is that what you're showing has converged. Right? So for some initial data, that would take an insane resolution to get to some decent level. So I've just chosen some initial data which are particularly convenient for my purposes here.
Okay, thank you.
Yeah, but the bottleneck here is resolution in order to ensure convergence, and precision is also extremely important. So this is a computation which is performed with Mathematica for the very reason that it allows you to deal with arbitrary precision real numbers. If you were to perform it with machine precision numbers, you wouldn't be able to do it. It would give you nonsense. If you wanted to take it to very high order, it would give you nonsense, basically.
Excuse me, I have a question. So can you go back to the previous figure?
Previous? Do you mean this one?
Yes. So no. Previous one.
12.
Yes.
Okay.
Well, yeah, I'm a little bit confused. So this n is the order of epsilon, right?
Sorry?
This n is order of epsilon, right?
Yes.
But now right figure is looking at t, right? So
no, because this guy here. Okay, so the point is the following. So if you assume that you have a one dominant singularity and that this answer is correct, right? Mm-hmm. This guy would be the inverse of this slope. Mm-hmm. So its curve here is give me a time, fix the time, okay, and compute the gradient expansion as a function of n. And now you take this time, you extract this slope, and in this particular example, that gives you the dominant chi, okay, which would correspond to this singularity here, which is the closest to the origin, okay?
Mhm.
And you plot that. Okay, so this is basically, so inverse slope of this goes here, inverse slope of this goes here, inverse slope of this goes here, and so on.
I see.
Okay.
Okay.
Okay. So this is more clear to you now. So also notice that this is function. This is a quantity which you compute at every time. It's a function of time, and this is this is a quantity which for a given time you get one different thing. Okay, so this is clear. No? Okay, great. So well, so just to take in stock, I'm going to sort of take some stock of this analysis, right? So I'm going to point out that this analysis allows us to make some comments on the origin of the gradient, of the factorial divergence of the gradient expansion. So first of all, when you solve the recursion relation that I showed to you explicitly, the nth term, this pi per n, can be expressed as a sum in which each term contributing to the sum involves the action of n spacetime derivatives acting on your elementary fields. This is by construction. And in the absence of nonlinearities in the constitutive relation, you can show that the number of these terms contributing at each order grows geometrically with the order, not factorially. So in this case, at least, the factorial divergence has to come from the growth of the derivative operators acting on your solution and not by the growth of the number of independent terms contributing at each order. Okay? And this is, you can think of this as being in line with the linearized hydrodynamics result that Ben discussed in his talk yesterday. So in that case, there were only a few independent transport coefficients at each order, whose norm grew geometrically. So the factorial divergence, when present, was totally due to the action of the spatial derivatives acting on the field you are evaluating the gradient expansion upon. Okay. Okay. So now, if you any comments, questions? If not, I'm just going to switch to another particular model in this class of BRS3 theories. So you have some question about what I just said, please speak up. Okay, no question, right. So now as promised in this morning discussion, I'm going to talk about this Denny-Noronha model. Okay, so I mentioned some highlights of this analysis this morning, but I'm just going to reiterate them here for those of you that were not present in the discussion session. Okay, so the observation I just made is not particular to this conformal BRS3 theory, and it would also hold in this. It also holds in this ultra-relativistic gas of hard spheres, which was studied in this paper by Gabriel Denny-Noronha and George Noronha in 2019. Okay, so this the model they considered is still a BRS3 theory, but apart from having a traceless energy momentum tensor, it also features a conserved current, which takes this form, in which n is the particle density. And the dependence of the temperature in the energy density and the transport coefficients on the hydrodynamic fields is different. So now the temperature is proportional to the particle density times the temperature. The energy is proportional to the particle density times the temperature. This is how you define the temperature. The relaxation time is inversely proportional to the particle density, and the shear viscosity is proportional to the temperature. And as this author showed, this system is remarkable in a sense that for Bjorken flow, there is a natural gradient expansion that you can consider in terms of the Nansen number, which for this system is time independent. And it turns out that this gradient expansion grows geometrically and can even be convergent for sufficiently low Nansen number. So it is natural to ask what our gradient expansion constructed out of as this formal power series in epsilon, how this object behaves in this particular model. So this is what I'm going to do now for Bjorken flow. So it turns out that for our construction, this property that these authors discovered is also true. So the gradient expansion in this model for Bjorken flow also grows geometrically and can even be convergent. And here I have an example showing this very fact for you. So what you see in this plot is this plot is the equivalent of these other plots that, well, that I have here. But the only issue is that I'm choosing a particular time. So this is basically the gradient expansion. Starting from some initial condition. This is for Bjorken flow, starting from some initial condition, and it's the gradient expansion at a given time. Okay. So a very, very nice feature of this model is that you can solve for the gradient expansion, for the coefficients of the gradient expansion in terms of the initial data analytically, and that would correspond to the green core, to the green dots. So the green dots are an analytic prediction. And what you see from the root test is that at large order, they grow geometrically, not factorially. Okay. So just as a cross-check of our numerical algorithms, we computed the same object, but using our method, just restricted to this particular example. And what you see here, the results that you get as you increase the temporal resolution are the black dots, the orange dots, and the purple dots. And what you see is that our numerical method is able to reproduce the analytic prediction, at least up to some point, which goes to the right as the resolution is increased. So this is convergent to the correct analytical prediction, okay? Which is that our gradient expansion in this system for Bjork and flow is geometrically divergent and not factorially divergent. And as I mentioned this morning in the discussion session, this fact follows from the combination of several inputs. So the first input is the dependence of the relaxation time with the particle density. So they are inversely related. This is extremely important. The second one is the particular dependence of the particle density with the proper time for Bjork and flow. So just so happens for Bjork and flow in this system, the equations of motion tell you that the particle density scales at the inverse as the inverse of the proper time. So these facts together imply that the proper time for Bjork and flow scales as the relaxation time for Bjork and flow scales as proper time. So this is the origin behind the convergence. Okay, this is the reason behind the convergence. Once you take into account that here the local temperature is given by a sum of several power laws in tau on shell, and that's it. And if you break any one of these three properties, this geometric growth to gradient expansion is destroyed and you recover a factorial one. So for instance, if you keep the Bjork and flow symmetries, but you change by hand the scaling of tau pi with n, for instance, you introduce here an offset given by delta, you get back a factorially divergent series. Or, and this is a sample we're going to talk about, if you keep the scaling of the relaxation time, the particle density, but you consider a different fluid flow, in particular our 1 + 1 dimensional longitudinal flow, this property would also be destroyed, and what you recover is remarkably similar to what we had before. Okay, so these plots are the exact equivalents of the plots I described before for conformal Bialis-3 theory, and you look that you see that their qualitative features are exactly the same. So in this model, the gradient expansion for Bjork and flow is convergent, but as soon as you consider a more generic fluid flow, you get a factorial divergence back. So in that sense, Bjork and flow in this model is fine-tuned in that sense. Okay, just that's basically the main point I want to make. And well, you can also check, as you remember, the plots that I have about the Borel plane singularities of the Padeo approximant of the Borel transform to gradient expansion. So you can find those for the initial data that we are considering here in this particular model, and you see that they behave as this formula predicted. But now it has the catch that the relaxation time does not depend on the local temperature; it depends on the local particle density, and you have to take this into account if you want to see the matching. But it's basically the same idea. So the equation predicts that the real parts have to grow in a precise way, while the imaginary parts are time independent. And now if you compensate your numerical data, for the predicted analytic behavior, you see the trajectory is collapsing, well, to some very good degree approximation into single points. Okay, so questions of this particular part here of this Denny-Colner-Ronya model?
So perhaps I have a question.
Sure.
Hi, Alex. Because like going back to the old computation of factorial growths in this ADS whole graph that we had with Michał and Przemek long time ago.
Yes.
So basically the factorial growth was associated with the appearance of those non-hydrodynamic quasi-normal modes, right? Yeah. So in a way, what it indicated was that the hydrodynamic degrees of freedom is not everything which describes the system, but there's some additional freedom of tuning initial conditions to excite those other degrees of freedom. And of course, they appear and therefore we cannot have really convergent expansion, because if we would have a convergent expansion, this would mean that everything would be contained in hydrodynamics, but there are some other degrees of freedom which are not. So now I wonder, could one turn it around? And since this nonlinear model was really like a guess of like hard spheres, could one say that then like hydrodynamics is complete in this sense, and therefore there's no place for additional degrees of freedom? So could one say that this like factorial growth or convergence of power law or geometric growth is related to the physical question whether we consider all relevant degrees of freedom or we are missing some of them out?
Okay, I don't have a clear-cut answer to give you. I basically share the viewpoint that you have expressed, and I think that's morally speaking, it's a morally speaking is the correct viewpoint that you have to take. But yeah, I don't have any more elaboration to. I don't know how to elaborate more on that fact. Basically. So I can point out several aspects of the Bjorken flow solution in Danico and Noronha. Maybe they're also helpful. So in this system, if you consider the local fluid temperature as a function of proper time, right? That is given by a sum of several. Well, I think it's 2 power laws in tau, right? So the time dependence is extremely simple. It's extremely simple. So you have basically it's tau to some power, which depends on the Nunsen number. You have 2 terms like this, and I think that's all for the temperature, for instance. So the question that confuses me a little bit is that I don't know, for instance, if you show that, if you throw that information to me, I don't know if you would be able to call the first power hydrodynamic and the second power non-hydrodynamic, right? But they would not be given by 1/tau expansions that would be complete. So in a sense, the 1/tau expansion in this model is very peculiar.
Okay.
At least for the temperature. For the pressure anisotropies is more involved, but for the temperature is extremely simple. Extremely simple.
So to elaborate further on the on Romel's question, so from the discussion that we had in the previous session, my naive understanding of these what happens in this model was that so in the system that Michal studied, in fact, you have these divergent series, and that divergence corresponds to these exponentially damped modes, which go as like e to the minus tau over the relaxation time. But then, of course, in this case, you're scaling the relaxation time also with tau, right? So it somehow kills off these sort of non-perturbative exponentially decaying modes. I think that's sort of what's going on in here. But you don't have these non-perturbative sectors, and the fact that the large tau expansion is convergent sort of makes sense.
Yeah, I would say that in this case, if I can write, wow, okay, this is going to be horrible. But anyway, if you imagine that the exponential correction that you have is something like, wow, d tau prime, right, or oof, okay, this is going to be complicated. But anyway, let's try to do it. So imagine that you have this exponential correction, right? Okay, so if you plug back into this sort of exponential non-perturbative correction to your grained expansion, let's say you're in conformal BRS3, right? And you plug back in the value, the correct scaling of tau pi with the temperature in that case, and then you put the large tau expansion of the temperature, right? And you compute this, that gives you the exponential of -3/2, inverse of dimensionless relaxation time times W that you had before, right? Plus the 1/W corrections, dressing this particular non-perturbative sector. But if you are in this theory for Bjorken flow, this object, due to the particular scaling of tau pi with n and the particular scaling of n with tau, it just gives you a d tau prime over tau prime right away, right, with no further corrections there. So it's just some exact contribution in this sense. So this is if you are able to think of the power.
So this is very interesting. So you're saying when tau pi is actually linear in tau, then you have a log which becomes
You have a log with some weight in front.
Yeah. Right. This is very similar to what happens in. So if you have a periodic potential in the one-dimensional quantum mechanics, right? Okay. So if you're expanding in small h bar in the semi-classical limit for the low-lying states. At the bottom of the well, you know, you have harmonic oscillator plus some perturbative corrections, and then you have instantons where, you know, you tunnel from one minimum of the periodic potential to the other, and then those are exponentially suppressed and go as e to the minus 1 over h bar, right? But if you're making an expansion for the high lying states way above the barrier, then that expansion is in 1 over h bar, and it is actually a convergent expansion. In h bar, but there is some non-perturbative physics that, well, non-perturbative that shows up there in the sense that so you have turning points which are complex, right? And so there is an action. There's an action between those complex turning points. And that action is in the sort of semi-classical regime, logarithmic in h bar. So e to the minus, the action becomes a power in h bar, okay, so and enters in exactly in the same way as the perturbative 1 over h bar sort of terms enter, but you can still distinguish in a way. So this seems similar, that somehow these non-perturbative modes, whatever they are, enter in the same way. I'm sorry, enter in the same way as powers, because your action is logarithmic in tau. Yeah. Okay. So this is interesting. So you might still be able to identify these non-perturbative terms, but they're sort of mixed.
Yeah. I don't really know what's.
Yeah,
I'm very sympathetic to the perspectives, to the points of view you're putting forward, but I don't really have a deeper understanding of this issue. I mean, I don't know how to think of how to, you know, translate the understanding that you would have when the series is factorially divergent and so on to this particular specific case, right? Yeah, right. I think that if you can use the same language, the same physical language, that's very, very nice. But yeah, I don't know how to do it.
Right.
Yeah, so any other questions or comments regarding this part? Okay, great. So I will continue. And okay, now I need to learn how to. Okay, does anybody know how to erase this thing?
Yeah, you have to click on like where you annotated earlier, and then there's like a.
This eraser thing. Okay.
No, there's even a better way, but.
Well, okay.
There's a delete. There's like a garbage can icon.
Clear. Oh, great. Perfect. Thanks. I'm still adjusting myself. Okay. Well, good. Let me take this out. Good. Okay. So I will conclude this part about BRS3 theory, and I would just mention several lessons that we can draw from it. So first one is the most obvious one, which is that the factorially divergent character of the gradient expansion extends beyond Bjorken flow. I think this is sufficiently demonstrated. I think at least I have demonstrated this point have provided sufficient evidence to demonstrate this point. And then the second one is that the relation between the singularities of the Borel transform of the gradient expansion in the Borel plane and the non-hydrodynamic modes of the system would stay the same as you would have in Bjorken flow, and in particular, the singularities in the Borel plane would obey this relationship here. So the comoving derivative, so the derivative along the flow of the singularity location would be controlled by the non-hydrodynamic quasi-normal modes evaluated at zero momentum at the local fluid variables like local temperature, local particle density, and so on. So I would say that it's natural, given the evidence we have as of now, coming from the boost invariant flow studies that Michal presented, and the linearized hydrodynamics analysis that been discussed, that this lesson would probably hold true in generic microscopic theories, such as holographic CFTs. But I would like to discuss a little bit about the second property. So if there is a factorial divergence present, are we guaranteed that chi would obey an equation of this form? And by equation of this form, I mean, is it guaranteed that chi, the singularities in the Borel plane, are going to be controlled directly by the quasi-normal modes, the non-hydrodynamic modes of the system, evaluated at zero momentum? That's basically the question. So this is a point I think we need to understand I think we need to understand how this relationship generalizes to general theories. And the reason I'm bringing this up is that because in BRS3, you can argue that this inverse relation is a consequence of the fact that the equation of motion for the dissipative tensor is actually an ODE in the proper time along the flow, right? It only involves the U mu d mu, right? So it's a comoving derivative, it's a material derivative along the flow. Right. But you wouldn't expect to have such a simple equation of motion, such a simple dynamical constitutive relation in general, right? So to conclude the talk, and just to elaborate more on these two questions, I'm going to comment briefly on how this relationship would be generalized to the ADS-50 case. So this factorial over power ansatz that worked so well in the BRS3 case can also be applied to holography. And we have done that, and without entering into technical details, which are of course important, and under the assumption, well, okay, so here you would put forward these ansatz for every metric component, let's say. So assuming that this chi function is independent on the metric component you're considering, and also assuming that it's independent on the real direction in the back, the end result that you get if you perform such an analysis, and this is schematically speaking, I'm not going to present the full result for you because it's going to take me to explain a lot of technical points I don't want to get into. But the result basically has this form. Okay, so if chi would obey a nonlinear partial differential equation, which is controlled by two kinds, it involves two kinds of derivatives. One is a common derivative, and the other is some sort of transverse derivative. So the way this derivative enters into the game is that if you evolve for a given amount of proper time on the flow, and then you stop, you would have some sort of hypersurface. So this derivative appearing here is tangent to this hypersurface, okay? But this is important, but it's not the crux of this analysis. So the most important piece comes in the form of this function, which is directly related to the quasi-normal modes of a black brane whose global temperature at a given position in the fluid equals the local temperature of the fluid, and so on, okay? And the important thing, well, there are several important things here. So the first one is that the factorial over power ansatz is not going to tell you which particular quasi-normal mode you should consider. And asymptotically, it seems that arbitrary linear combinations of solutions of this form would be allowed, you know, to control the large order behavior. So as I said, we don't have any understanding of how to relate this singularity structure and the number of singularities and so on with the initial data that we don't know. But from this result, you see that if you were to consider that your system is boost invariant, then you would recover what we had before, because then this function, this derivative would vanish, and this function would essentially be given by a quasi-normal mode at zero momentum, okay? So the reason I'm bringing up this formula here is because it suggests to you a very natural generalization of this feature found in BRS3. Now we have seen that for 1 + 1 dimensional flows is general, and also in Bjorken, which is known in ADS-50, right? So that's basically, and of course, the lesson you have to draw is that in general, this chi function would obey a nonlinear partial differential equation, as I said, which is sensitive to the form of the dispersion relations at finite momentum and not just at zero momentum, as it was the case before for Bjorken flow or for BRS3. Okay, but please take this result is just some analytic result, and it still has to be cross-checked with a proper numerical computation, if possible. But I'm bringing it up because it's thought-provoking, at least to me, and it suggests some how the general story could be. At least it gives you some hints of what it could be, the general story behind this. And this is basically my last slide. So my next to last slide. So it's also just mentioning feature directions, it would be interesting to, of course, bring this ADCFT analytical analysis to the same level of rigor as the BRS-3.1 by complementing it with some numerical results. And it would also be very nice to explore these ideas in other models, such as particular kinetic theory. And I think it would also be interesting to generalize, to find out whether it's possible to generalize BRS-3 in such a way that the equation of motion for prime nu not only involves moving derivatives, and so you can build a simplified model which reproduces this feature that the ADS-CFT analysis suggests. And I would also say that, to me at least, it's fun to wonder about the consequences of this function of this chi, which again controls the singularities of the gradient, the singularities of the Borel transform of the gradient expansion. The fact that it's sensitive to the quasi-normal modes at finite momentum suggests to you that maybe there is an imprint of the mode collisions that Ben discussed in his talk into the, let's say, space-time evolution of these singularities in the Borel plane. So they would correspond to some, I don't know what they would correspond to. Maybe they correspond to some reorganization of the trans series, some sort of different, but it would be nice to understand whether that's possible first, and second, whether that has any physical meaning, so that you can maybe ascribe novel physical meaning to mode collisions, for instance. That would be something that I would definitely love to understand, whether it's possible. And as a final comment or a final thought, I think it would be very interesting to find whether the constitutive relations can be upgraded in a systematic way to a trans series in epsilon to incorporate the effect of some of the non-hydrodynamic degrees of freedom present in your microscopic theory. And given Mauricio's talk on Wednesday, I find very entertaining to wonder whether such a construction could be thought of as some sort of flow-dependent transport coefficients in your constitutive relations and some sort of non-Newtonianity. Okay, so with these thoughts, I would conclude the presentation. I don't know how long it took me, actually. Well, I think it's pretty decent enough. Yeah, so if you want to discuss these points or you have any other comment or questions, I would be glad to engage in some discussion.
Oh, excuse me. So I have again the question about the epsilon. Okay, so in that case, what is the definition of a non-hydro mode?
A non-hydro mode is a mode. Okay, so
non-hydro, yeah.
From the perspective of the okay, if you perform the epsilon expansion in, let's say, position space, right? That has a natural translation into momentum space, right? So from that perspective, a non-hydrodynamic mode, which is a mode whose dispersion relation has a frequency that doesn't vanish in the zero momentum limit, right? Automatically becomes a mode which is non-perturbative in epsilon, essentially. Whereas a hydrodynamic mode is perturbative, is at least not non-perturbative, right? It can be a constant or it can be order epsilon. Basically, that's it. That's it. If you perform the epsilon expansion in position space, in momentum space, you're automatically gapping by some inverse power of epsilon or your non-hydrodynamic modes. So it's a way, if you want, it's a way of reorganizing the modes in such a way that you keep the hydrodynamic ones and you throw the rest out. Yeah, that's the effect that it would have from a Fourier space perspective, I would say.
But okay, in your case, it's x over epsilon, right? So in that case, you are looking at only the infinity, right? So if you have a kind of the 1 over epsilon in the exponential, so which is the origin of that? X or tau or something.
So you're asking me whether if I have some non-perturbative correction in the exponential?
Yeah, like exponential, let's say exponential something minus some constant over epsilon. But now you are scaling at the same time. So which is the origin of this kind of epsilon? So for example, t or x or something.
Yeah,
in the original sense.
That I would interpret as a transient contribution coming from some non-hydrodynamic mode. Yeah, that I would interpret in that way. I would interpret non-perturbative. Yeah, I think you can, at least at the level of linear response theory, you can draw a precise correspondence between non-perturbative contributions in 1 over epsilon, as epsilon goes to 0, and non-hydrodynamic contributions. Yeah, at least linear response theory, you can draw a precise map between these two kinds of objects. At the nonlinear level, what I said is pure speculation. I don't know the answer to that question. I don't know whether that question has an answer, right?
Okay.
But yeah. Okay. But yeah, I hope you can come to terms with the idea of this epsilon parameter. I hope at least I have clarified some of your doubts.
So yeah, I mean, why didn't you start with just a double expansion using T or T and X, for example?
So you're asking me?
Why didn't you? Yeah, why didn't you start with just a expansion of T and or X? Because it's gonna be double expansion, right? So if you have a kind of the non-part of the
you mean why am I? So if I understand, you're asking why do I scale T and X in the same way?
Yeah.
Because okay, that's a choice. That's a choice which is up to you. Because I want to count. I want to count temporal derivatives and space derivatives with the same weight, right? But that's a choice. That choice is not a, I could have chosen a different scaling if I were interested in some more. Okay, for instance, in this talk this morning, it was mentioned this paper that we wrote with Michael Heller, Michael Spaninski, Victor Svensson, and Ben Withers in November, in which we discussed this inhomogeneous space-time scaling in the telegrapher's equation. And the reason that the scaling there was inhomogeneous, I mean, so space and time scale differently, was because that we were interested in the physics of the late time behavior, which is diffusion. So if you are aiming at those particular physics, this is the scaling that would extract this physics for you, right? While at the same time making all the non-hydrodynamic modes of the system non-perturbative. Yeah, here I'm not interested in those particular physics. I'm just interested in counting derivatives with equal importance given to time derivatives and spatial derivatives. So I choose the homogeneous one. That's it. But it's a choice. It's a choice. It's not absolutely no way this is. I mean, it's a choice that it's imposed to you by the physics of the problem you want to study. I mean, there is no underlying reason other than that for choosing one over the other, I would say.
Okay. Yeah, thank you.
Can I ask a question? So when if you were hoping to analyze Borel plane from the point of view of situations where your hydromodes really, you need to analyze them as dependent on K. But if you have your hydro and non-hydro modes both depending on K, you have all of them will be for any value of K, all of them will be exponentially small. Isn't this the case?
You're talking about that it wouldn't be, there wouldn't be a natural distinction between them?
Meaning so the perturbative series is associated to the hydro part.
Yes.
Which has no exponential.
Yes.
But if you start having momentum dependence, then this wouldn't be true anymore, right? You'd have an exponential there as well.
I would say so. Okay, if you're thinking about this particular functional here, right? This can be associated with any. This is constructed out of the. Okay, maybe I should have gotten into more technical details, but this is makes no distinction between being hydrodynamic or being non-hydrodynamic. So you don't have to make that distinction in order to recover an equation, this sort of an equation, basically. That's a point that maybe I should have mentioned. So
how would you analyze the Borel plane singularities? What?
Yeah. Okay. So let me explain the way. The way to go here is that the thing is that this. Okay. So this equation here, the black brane in which you have to evaluate this functional, right? Or the black brane construction, the dual gravitational construction that gives you this functional is a boosted black brane. Okay. So so it might be the case that whatever was not gapped in your original, rest frame now, by performing this construction, becomes gapped. So I don't have a clear understanding of that point yet. Right? So these are quasi-normal modes which are obtained for a particular dual gravitational construction, which involves it involves a boosted black brain, which is boosted in a particular way depending on the fluid flow, right? So I still don't know how to translate that directly to the more standard quasi-normal modes of some, unboosted black brain at rest and so on. So yeah, I think it's a good point, but I wouldn't be able to tell you, oh, this standard quasi-normal mode you're thinking about would map to this particular function, right? That I don't know how to do. But I think that the functional form that this equation shows is quite robust. I mean, this is what the analysis suggests to you. So its success in BRS3 would suggest that it should also, well, I mean, it gives you hope to believe that it would also work in ADS-CFT. So my only point is to illustrate that you have at least some evidence to believe that the evolution equation obeyed by these objects here, in terms of your, the evolution equation that your microscopic theory imposes on these objects here, can be way more complicated than the BRS3 one, or the one in Bjorkenfeld for that matter. Okay, so it's just to trying to leave the, I wouldn't say the prejudice, of course, the preconceived idea that quasi-normal modes at zero momentum play a privileged role. I mean, this analysis suggests that they note, and for more general flows, how singularities evolve in the world plane, at least for this particular kind of gradient expansion, can be extremely more complicated and potentially more interesting, as I said. I mean, because now you can consider that they can have all sorts of interesting dynamics, because the dynamics I showed to you were sort of trivial, right? They just move to the right, and that's it. I'm saying that in general, you can expect that this behavior is way more intricate. So at least that makes the problem more interesting to me, right? Also more difficult to understand, of course. But.
Well, thank you. We can also, meaning if you think that people will be happier just to have informal discussion now, we can just stop the recording as well.
Oh yeah, sure. I mean, I'm just speaking. I don't know how long have I been speaking. So, well, okay, it's probably already.
So perhaps I just stop the recording and we can chat in any case until we. So well, again, but thank you, Alex, for the last discussion, and thank you everyone also for joining. And all the questions in between. So this, yeah, at least as far as the recording goes, finishes our focus week. Thank you.
Great. Thank you so much.